Okay, thank you. So now we're about to hear about dusty AGB stars.
Okay, is it okay?
Yes, thank you.
Okay, well, thank you for the invitation. Well, I'm missing the fun part of not being with you. It's a pity. But I will present some recent developments we've made in Phantom that concerns the modeling in winds in stars in general, and also of dust in AGB stars for these dusty AGB winds. So this work has been done in collaboration with many researchers. Well, you know already one of them, Jolene, who gave a talk on Monday. But there are many people in Leuven, and also this dust formation in the envelope of AGB stars has been used to model a common envelope evolution, and you will see a talk by Miguel following mine later on and apply to a common envelope. So what are the motivations? So I'm moving recently to SPH, but I am mostly a stellar evolution researchers. And I studied AGB star for many years, and they are very interesting because of for many reasons. And one of them is because of the nucleosynthesis. They produce some heavy elements for instance, the S elements or the fluorine. And also, as Jolene mentioned in her talk, they have extended atmospheres where they can form molecules, and these molecules, they can glue and form dust. And that dust is a driver for these strong winds. And so this is for isolated AGB stars, but as Jolene showed, if you put a companion, then the entire morphology of the circumstellar environment is modified. You've got the appearance of shocks, of spirals, of structures, and if you have eccentricity, it becomes even chaotic. And that can influence also our estimates of the mass loss, which is crucial for galactic chemical evolution, for instance. And well, if you have a companion, well, you may expect interactions. In one of the previous talks, it was mentioned that, well, massive stars, they interact. Well, 70% of the massive stars interact eventually. And AGB stars being convective, if you start transferring mass to a companion, then you may end up in very bad situations like common envelope evolution. Or if you have distant stars, then the companion can be polluted by the winds of the AGB. And since these AGB stars they produce a unique nucleosynthesis, well, you can trace this mass transfer by analyzing the composition of these peculiar stars. And one of the motivations that started this project was try to understand this diagram. So it shows, well, the observations of barium stars. So barium stars are main sequence or subgiant stars which show barium, and barium was produced by the AGB companion, which is now an extinct white dwarf. And those are the observations, and the modeling is in blue. So you see that the theory is doing pretty well at avoiding the observations. The short period systems, while tides are strong, so they tend to circularize, and the long period system, because the AGB is losing so much mass, well, the separation increases, so the period increases, and those stars, they move at longer periods. But most of the observations, they center, you know, well, in that region where we expect almost no stars, and they show very high eccentricities. And that was the initial motivation, because I was doing stellar evolution, trying to understand this, and one decode cannot understand what's going on. So I moved to SPH, and to try to understand this process and many others, the first thing was to develop some wind module in Phantom, and also some dust, because dust is relevant for driving the wind. So if you include dust in the equation, that will modify the hydro equations. The first thing is that well, dust is opaque, so it will absorb the photons, and that will trigger some, well, that will lead to some radiation force, which is shown here. And well, if you consider, well, the radiation force and the gravitational force of the sync particle of the mass-losing star, you will see that the radiation force just acts as lowering the effective gravity of the star. And this parameter gamma is also referred to as the Eddington factor, is proportional to the dust you see here. And sometimes you may have an L is the luminosity of the star, and you may have an attenuation of the stellar luminosity. So you need also the optical depth. So you see that as soon as you inject dust, then you have a lot of problems. You have to evaluate the opacity, the optical depth. And also, well, the dust may have a different temperature from that of the gas. And that will induce some heat exchange between the gas and the dust. And that will modify the heat, well, add a term in the energy conservation equation. And this is, for instance, one prescription where you have kind of a diffusion of heat between the gas and the dust. So we also have to estimate the dust temperature. So you see, the problem is getting more and more complicated. So how to estimate the dust? Well, we can rely on radiative transfer codes like MC-FOST, but it's time consuming, or you can use some analytical expressions like this one where you have a dilution of the flux plus an attenuation. But the first thing to understand, to model all of this, is to consider the wind. So how do we model the wind in phantom? So what we do is we solve the steady 1D wind profile. So it's the Parker solution. So you fix your mass-losing star is a sinc particle, and you specify the radius of your star. So that's what we call the injection radius. Then you specify the temperature of your wind, that gives the pressure initially, and the mass loss rate. And with these quantities, well, we can estimate the velocity profile and the internal energy of the particle. And this is what is shown here with these black lines. This is the velocity and the distance. So the black line is the semi-analytical solution, so solution of these, and all the dots are the SPH particles. So when particles needs to be released, we assign to these new particles, created particles in the domain, the velocity that is given by the wind equation, as well as the internal energy. So what we also implemented is here some boundary shells, so that it provides the pressure to push the particles outwards, because otherwise all these stars will fall back onto the sinc. It's just a vacuum. And how we distribute the particles on the stars on the surface of the star? Well, what we do is to tile the sphere using triangles. So that leads to these isochahedron surfaces, with, you see here, increasing order. So it means that well, the number of particles you can eject at a given time is quantized. I mean, when you go from one order to the next, you see that it's not a random number, so it's a fixed number. And what we do to improve the simulation is that between two ejections, we rotate the two shells, so that's smooth out the artifacts and avoid some features. The second point that we need to model, as I mentioned, is the dust. So dust is a very complicated process. So you start with atoms that eventually make molecules, and those molecules, they stick together to make seeds. And only when you have formed those seeds, so this is the nucleation phase, and when you have these seeds, then these particles will glue onto that seed and grow, and that's the growth phase. So what we do is we consider, when you have a seed, well, it can grow by the addition of what we call monomers. So those are the dust building blocks. So here we only consider carbon-rich chemistry. So you just add some carbon-bearing molecules. But to estimate all these molecules, well, you need a chemical network. So this is what we do. We follow the abundances of 7 atoms, and we consider 25 molecules. So you see, carbon is you can be locked in oxygen, so that removes a lot of carbon, and then, well, you estimate the various abundances. And once you have that, you can estimate some properties of the dust. And how do you do that? Well, we use a very complicated theory, it's the moment theory that was developed by Gale and Sedlmeier. And the goal here is not to follow the grain size distribution F, but to evolve its moments. Okay, so this is the moments of order I of the grain size distribution, just like in a radiative transfer, you calculate the order. And within that theory, for instance, you can get, if you know the first moment and the 0th moment, you can have an estimate of the mean grain radius. K2 over K0 gives you the mean grain surface, and K3 gives you the opacity. You remember in the previous slides, to get the acceleration, we need the opacity. So all this business to get kappa, to get the kappa dust. And how do we follow the evolution of these moments? Well, this is the set of equations. So we have the nucleation and we have the 4 moments starting from 0, 1, 2, 3. And all the other quantities like the rate of the J star S or the time scales, they all depend on the chemistry. So once you know the chemistry and the thermodynamical conditions, you can evaluate this. And at each time step, we have to evolve these moments. So we know how much carbon is locked into the dust and so on, and proceed the evolution. So compared to other simulation, each SPH particle now carries the information about the moments and about the nucleation rate. So we tested our implementation. So this is the nucleation rate. So this is the rate at which you form these seeds, which are the starting point of the growth. And so this is our estimate of J star, and this is what Gale and Sedelmeier found in 84. So it's very similar. There are some changes because we use updated chemical constants. It's working very well. Then we applied this dust process to a wind, and I show you here illustrate in this plot the effect of dust. So this line here is when you do not consider dust, so you have a typical velocity. And as soon as you trigger all this business of dust formation, you see that when kappa, the opacity, rises, then suddenly you have an increase in the velocity. So there is this is the acceleration provided by the radiation force. But also because we have the small chemical network, the mean molecular weight is changing, and this increase in the mean molecular weight is due to the change in the formation of H2 molecules. So, taking into account this, the network also has some impact on the equation of state. Now, if you had a companion, so this is the mass-losing AGB star, this is the companion, and that shows the same quantity, the nucleation rate, and we see that dust is forming in the wake of the companion, where the density is high, and where the density is high. It's the main reason. Also, that this is something that has been recently developed, is still under progress. We implemented this dust formation into common envelope evolution with the group of Ursula De Marco in Macquarie. And this is the evolution of the common envelope at different times. And the color here represents the opacity. It's a log scale. So the red is where you have high opacity. And you see that during the evolution, you start forming a shell of dust that will eventually modify the flow. But I won't spoil Miguel's talk because he will be talking about it later on. This is also done with Luis Bermudez, who's joining Macquarie very soon. The next thing that we need to do is, you remember one of the quantities to estimate the optical depth. So what we do, we implemented a ray tracer algorithm, which is based on the Magritte code that you heard of in Jolene's talk, that is developed in Leuven. And basically what we do, we use this package, which is called HillPix, and it pixelizes a sphere. So you define an order, and that gives you a number of pixels on the sphere, and HillPix through rays in all these directions. And what we do is to integrate the optical depth along those rays. I won't go into the details of the algorithm, but along each of these rays, you know the optical depth. And the power of HillPix is that when you have a particle, let's say the pink particle here, HillPix gives you instantaneously the neighboring, the closest rays. So these 3 red one and the blue one. And what we do is basically to build a 3D map of the optical depth. And for each particle, we interpolate in that volume the optical depth. So we know the optical depth of each particle. So this is what we did. And so this is some recent simulation done by Mats Esselders in Leuven, in collaboration also with Jolene. So the solid line are the semi-analytical solution. So this is the free wind. So it means that gamma equals 1. So it means that there is no gravity. The star is not, well, the particles are not feeling the gravity of the mass losing particles. And in blue, this is when we include all the business. So we include the dust formation. We use an approximate, it's just for testing at the moment, implementation of dust, which is called the Bowen, but Miguel will discuss it in more details. And what we see is that, well, initially, well, the gas is hot, so dust is not forming, and because of the gravitational pull of the star, well, the velocity decreases. Eventually, the temperature drops, you start forming dust, and then suddenly you have the kick. Yeah, the radiation pressure allows the particle to be ejected. And you have that curve, and you see that you cross the escape velocity, and the particles are just released. This is also an output of that simulation. When you put a binary companion, you see that so that shows the optical depth, and you can see, for instance, the shadow cone that is behind the companion. So this is the mass losing star, and you have the shadow. So you can calculate the optical depth. So you have an estimate of the dust temperature, and you have all the quantities you need to get a more realistic simulation. So I go now to the final slides about the prospect and the future developments. So radiative transfer is something that is essential, because depending on the dust temperature, well, you can have cooling. And we showed before in that slide, you're able to launch the wind because the cooling is efficient. If the cooling is not efficient enough, the particle will eventually fall back onto the star. So you need efficient cooling so you can form dust. So this is something that needs to be estimated, and to estimate cooling, we need to have a good estimate of T-dust. And one of the developments we are undergoing with Daniel and Christophe is to couple MCFOS with our dust business. And the idea is that in the nucleation theory, we have the grain size distribution, well, the moments of the grain size distribution. Can we, from those moments, derive what is the grain size distribution? Because this is something that MCFOS needs to estimate the spectrum and all the quantities we need. Also the cooling, this is essential. Well, it's related to T-dust, and this is something we are doing with Daniel, testing the different numerical schemes, and also with Leuven implementing some additional cooling, well, like molecular cooling, line emission cooling. Pulsation, this is something I did not mention, but it's a complex problem. It's hasn't really been done, or when it has been done, I could not find the detail that tell me how it's done. So, but it seems to be a quite difficult problem. Chemistry, that has to be expanded, because at the moment we only consider carbon-rich chemistry. And for instance, Jolene showed very nice ALMA observations, and Tessa as well, and they are for oxygen-rich. So we have to adapt the chemistry or a small chemical network to deal with oxygen-rich stars. And also, if we improve the chemistry, we can trace the molecules that ALMA detects, because we have only a small sample, and also get some good some cooling rates. There is also an aspect, because we have gas and dust. Those are two fluids. Well, we expect them to be strongly coupled, but that can also induce some have some effect on the hydrodynamics. So this is something that needs to be studied. So all these developments aims at better understanding these ALMA observations that we have a better estimate of the mass loss rates, and better understand those binary interactions, especially why are those biome stars showing so high eccentricities. Also, it's important for common envelope, can dust help ejecting the mass? And if you include dust, what is the optical counterpart of these common envelope evolution? So there are many projects, and I mean, the wind can be applied to any stars, not only AGB stars. You just have to compile with the wind setup, and you will have the parameters, and you can play with it. You can, you can use a massive star. You don't need all the dust business as well to play and have fun with it. And I think I will stop here. Thank you.
Thanks for a really interesting talk. Does anyone have any questions?
I've got two to start with. One is, can we have a copy of your cool logo? I think it should be the new logo.
Yes, yeah, it's nice, huh?
We need more stickers.
Yeah, it's the spirals.
And the other question, which is a science question, is we're using this.
I don't know if I can answer.
Well, we're using this dust formation to form dust when the temperature drops below 1500 Kelvin. But would it naturally work the other way? So, for example, in some of LE simulations, we want to destroy dust when the temperature goes above 1500 Kelvin. So can we just use the algorithm, same algorithm in reverse?
Well, yeah, no, this is not yet implemented because it's a little bit more complicated, but you're right. Especially if you have shocks going through a dusty environment, you would expect the shock if the temperature is high enough to dissociate all the dust grains. And so no, this is also a good point, Daniel. Yeah, it needs to be implemented. At the moment, this can only grow. It's not destroyed yet.
I have a third question. I mean, the other one would be, I mean, your moment method is very similar to what Stefan and Jeff have been doing for dust growth in protoplanetary disks. Do you think we could use the same set of equations for dust growth in disks?
Well, I have to be more acquainted with their formalism. It's a bit different because here it's the integral of is the moment. So it's the integral of the grain size distribution. So you don't have access to the grain size distribution, but only to its integral. So I don't know how you can go from one quantity to the other. So these kind of inverse problems which are not easy to tackle.
So right now we have a method, the dust growth thing, which is coupled to the drag. So the dust can decouple depending on its size. But you have something, so these two methods are very similar, and I'm aware that we've implemented them in completely independent ways, which maybe should be joined. But that's maybe a longer project, but it's a good discussion to have.
Well, it's a good opportunity for me visiting you.
Yes.
Any more questions?
So I apologize if I missed this, but when did you consider, because you were talking about the interaction with the binary companion, so did you consider whether this could actually be used to simulate wind Roslob overflow in AGB binaries?
Yes, indeed. Yeah, that's the goal also, because this eccentricity, this high eccentricity of these biome styles, we expect that is due to the not Roslob overflow, because that would lead to common envelope, but to some wind Roslob overflow, and that would induce some eccentricity. Yeah, that's the underlying goal as well. Yes. Yeah.
Got it. Sorry.
Let's all thank Lionel again for a great talk.
Yeah. Thank you.